One major priority in radio astronomy is understanding the early universe formation history. Although the cosmic microwave background, or CMB, that results for the Big Bang is well measurable, the epoch that followed is not. This period is also known as the Dark Ages. However, one can infer Dark Ages characteristics by looking at the differential temperature between the CMB and the cosmic dawn, the epoch where the first stars started to form, sparking the epoch of reionization, which led to the full reionization of the universe. Understanding these epochs can lead to a wealth of information and give us more insight in the formation history of the celestial bodies we see around us today. One way to probe for these first stars, for example, is by probing the 21 centimeter spin flip transition line from neutral hydrogen, where a change in electron spin state emits a radio wave of 21 centimeter wavelength. However, measuring the 21 centimeter line is not trivial, as it's formed by extragalactic and galactic foregrounds before receiving it with a radio telescope system. It is hard to disentangle these foregrounds, as they are around 3 to 5 orders of magnitude higher than the signal we desire. One way to combat this is through the generation of multiple sky maps, spanning a wide range of frequencies and angular scales. These maps can then be used to generate a foreground model to abstract from the 21 centimeter background signal. However, although smaller angular scale point source foregrounds are relatively well defined, low frequency diffuse foreground emissions, especially on the southern hemisphere, are not. This is mostly due to the complexity of solving the three-dimensional interferometric measurement equation, which is often simplified using a flat sky approximation, allowing one to Fourier transform between the visibilities the system sees and the intensities in the sky. However, this results in a loss of wide field accuracy. As a result, we are forced to use more complex methods to image the full sky, such as mosaicing, which is often a time-consuming and strenuous process. Instead of assuming a flat sky, one could also use spherical harmonics to solve for the measurement equation instead. Much similar to how the Fourier series operates on the boundaries of a circle, spherical harmonic-based functions operate on the surface of a sphere. These basis functions can be split up in three distinct types: zonal, tesseract, and sectoral harmonics, which depend on the spherical harmonic order L and rank M. Shaw et al. Noted that when looking at Earth's periodic rotation over a sidereal day, one could notice sectoral harmonics operating in the same rotational plane. These harmonics are only rank M dependent and do not mix on the sky. We can utilize these characteristics through employing wide-field, center-pointed radio interferometers performing transit interferometry, measuring the sky passing overhead, whilst maintaining exact wide-field effects. Fourier transforming the visibilities with respect to M allows us to describe the visibilities as M modes. If we then also expand the beam transfer function and sky into spherical harmonic coefficients, we can reduce the measurement equation to a simple linear equation. Solving for the sky in this case would simply be inverting the equation. Using this method with the Engineering Development Array tool, a wide-field radio telescope in Western Australia, we present a 159 MHz M-mode generated sky map. This map is created with two 24-hour observations to remove the sun from our sky image. The map has a 3-degree angular resolution and is supersampled on a 1-degree pixel grid. The Northern Hemisphere is fit using a rescaled version of the updated desourced Hessel map by Ramazayas et al. This map is the first in a series of EDA2 generated diffuse southern sky maps, with goal to help better constrain a diffuse foreground model, and will be made publicly available once published.